Right, so welcome to lecture number 2. A quick recap from yesterday. We had talked about the applications of fluid mechanics. We talked about what fluid mechanics is. And then I briefly talked about the course content, what is expected in this course. So we'll continue from there. Okay, so we're still talking about the introduction part to this course. So one thing I particularly wanted to mention about is staying motivated and staying informed. So this is something I talk about in all my courses. So if you want to know about the latest developments in a particular field, that gives you a special interest while studying that field. That has worked for me in the past as a student, so I recommend that to the students I teach as well. Well, try it out if it works. So a couple of ways to stay motivated with the subject. Um, One is to get in touch with the latest research. So what exactly is happening in the mainstream in this research? So for that, you can, I gave you the FIFD website. So websites, as I mentioned, you have YouTube videos of the latest stuff that's happening. And nowadays with subscribing to videos, you will get latest updates as well. And then there are many websites that talk about the HPC applications. So you can have these email newsletters where every day or every week you'll get some summary of the latest applications in high performance computing in the field of fluid mechanics. Then you have CFD websites. So lots of stuff. So just register there and keep going through that material on a regular basis, and you'll start liking the field because you'll realize that this field has a lot of application in the latest world. The other way, the one that I particularly enjoy is movies. So for example, there's a movie called Armageddon. You may have heard of it. So this movie is about. I'll not give you any spoilers, but it's about the Earth's core. There's a metallic core. So that core is liquid, and that liquid core and that liquid keeps circulating. That creates a magnetic field in the Earth's atmosphere. So that core stops rotating for some reason. Science fiction, of course. And then people think about drilling a hole into the Earth's surface and then restarting the core rotation. So that's a fluid rotation that they would want to start again. So some ideas that you will enjoy while studying fluid mechanics. Another one is it's called Twister. Many movies, of course, related to engineering, science, and so on. Twister is where they want to study, a group of scientists want to study the flow in tornadoes. So they want to do some experiments and very risky experiments. So they want to put lots of small, low-cost sensors so that they can track the whole trajectory of tornadoes. So these are fun as well, so that they'll also keep you motivated with the subject. Next is popular science magazines. Again, I particularly enjoy these. So there are many that I regularly go through. For example, Popular Science magazine name by itself. Then you have Scientific American. Then New Scientist. Okay. National Geographic. Fluid Power. That's more technical. Then BBC has a couple of magazines. There's a Discovery magazine. Then Science Focus and BBC Earth are the ones. Popular Mechanics. Okay. So you can subscribe to websites where all these are available, and they're not very expensive anyways. So this again, rather than going through random useless stuff on the internet, you can actually spend a good quality time here. And again, you can simply browse through things rather than going and read whichever article you enjoy. So I got I got magazines as a demo, the ones I've subscribed to. Okay, so this one's called Fluid Power World. So let me demonstrate that to you. Okay, so this will talk about the latest development in the industry, and you'll get a lot of contacts about industrial companies that work in similar fields. Okay, so they talk a lot about this is fluid power. So this is power generated using fluids. So a lot of hydraulics and pneumatics and so on. But you will see that very interesting stuff and very technical stuff is also included here in terms of what's happening in fluid mechanics, or some fluid mechanics circuits, so on. So even if you don't want to read it, do browse through it, and you can always share it with your friends if you get some subscription or something. And if you want a magazine, let me know. I'll share one with you, the ones I have subscribed to. So here, for example, in food processing industry, they're talking about how to use the idea of suction to hold products in a production line. Okay. So lots of interesting stuff. So there's another one called, for example, Scientific American. It's another very popular science magazine. So here, what I do is I go to the index and then look for which articles. For example, this nasal spray. So this could this could be something to do with mechanical engineering and so on. Um, Oxygen shortages delayed rocket launches. So oxygen and rockets, so definitely some combustion happening here, some fluid mechanics. So then I would just mark it with a highlighter and then go through it in my own time. Okay. Yeah, make it a habit. You'll and that habit definitely will stay with you for a very long time. So I made this habit of reading magazines related to fluid mechanics when I was a student, undergraduate student. There used to be library where hard copies of magazines were there. I mean, not this kind of a variety, but one or two magazines every few months, like were delivered. So you just go there, sit and browse through the magazines. Okay, sci-fi novels again, very interesting hobby that you can develop. So there's if anybody has read anybody has seen the movie called Martian by Andy Weir. There's a couple of science fiction novels by this author. Michael Crichton is another one. So they'll write stuff which has a lot of real engineering in it. Definitely there's some level of fiction, but beyond that, most of it is feasible engineering that they talk about. So that will be interesting. History of science and maths is also very interesting. Um, okay, so many books are available. For example, in mathematics, if you read about Fourier, Joseph Fourier, or Leonard Euler, or Cauchy. Okay, so all of them have contributed significantly to fluid mechanics. So you should definitely read about the history, the kind of times they were in. They were in difficult times when survival was at stake. So how these people worked in mathematics and many scientists as well. So do read about it. There's a very nice book called Chaos. It's not a fiction. It's more of a popular science book. So do read it. It's about turbulence. Very nice history of how turbulence has affected the way we have developed in research, and how chaos theory in mathematics or physics is linked to what happens in day-to-day world in other fields of science as well. Again, then you have these documentaries available on Discovery app and all these things. So I have subscribed to Discovery app, and I go through these documentaries once in a while, which are also quite interesting. Right, so there's plenty of stuff to stay motivated. Okay, so whenever you feel that you are getting out of motivation, do explore these things. Right, so let's start with the technical content now. Now that we've talked a lot about soft stuff, so we will start with the introduction is split into two parts. The first one is going to be what you know about fluid mechanics, what has been fluid mechanics to you till now, and then we'll talk about some very basic ideas of fluid mechanics that are very important and that you definitely should keep with you before you, I mean, for the whole semester or throughout your understanding of fluid mechanics. Okay, everything would be based on those foundational ideas that we'll discuss in the introduction as well. So again, we start with what is FM fluid mechanics that has been taught to you in school. So that is where you were introduced to fluid mechanics, and that's your latest um, understanding of fluid mechanics as such. So in school, most of the fluid mechanics for us has been to do with statics. It's mostly statics. So for example, Pascal's law. So this has been taught to us. So I did here. The idea that the pressure transmits extremely fast. So if you have a connected fluid and you make a change to pressure at one place, then it will transmit, I mean, in an enclosed pipe system, then it transmits very fast. And the idea gets utilized in the design of hydraulic jacks. Right, so you can use so pressure is force per unit area, and this is, I'm just writing stuff and discussing stuff that you already know. And if we're talking about statics here, so if there is a pressure difference in a fluid, then the fluid will start to flow. So for statics, the pressure has to be the same everywhere. So if you have a hydraulic jack which looks like this, the pressure is force per unit area. So the force that you will get will be pressure times area. So more the area, more the force. So you can have a jack here, and then that results in which requires lesser force, and then you can generate a larger force by a larger area. Okay. The other one that you have learned a lot about again in statics is these U-tube manometers. They were mainly for practicing the skills of solving problems with hydrostatics and so on. So you had these interesting, intricate designs of tubes. And then you would study that there's one fluid, and there's on top of that there is another fluid, and so on, to calculate the pressure at different points and height of fluid at different points and so on. Then you've also learned about energy conservation. That's called Bernoulli's theorem. Okay, so the conservation of energy. So the total energy in terms of kinetic energy plus potential energy plus pressure energy is equal to constant. This is something that we have learned. So if you have a water cannon, that is used to disperse mobs and so on. So this water cannon uses the idea of high kinetic energy of water. So lots of energy there. Can do a lot of damage as well. Potential energy, dams, or your water tanks, they use the idea of high potential energy. So you can store that energy in water. So when your power is available, you can transport the water to a tank or a dam. And then when you require that water in your pipes, you can simply open the valve and the water flows down. So it's potential energy gets converted to kinetic energy. Then pressure energy. For gases, for example, you have gas cylinders. They store energy in the form of pressure energy. So again, a lot of energy. If you open the valve and change the pressure to atmospheric pressure, then there is a lot of kinetic energy that gets generated. So for ideal fluids, that is the fluids that have no viscosity, you can balance these over a streamline. That is what you have learned till now. So you have applied this for solving many different problems as well. The other idea that you have learned about is Archimedes' principle, or the idea of buoyancy. So you have learned that if you go into a swimming pool, you feel lighter. So the idea of apparent weight. So if you have a body which is floating in liquid, then it experiences a force called force of buoyancy, and this force is equal to the weight of liquid displaced by this body, the solid body. So this liquid that the body has displaced, which should have been here, that weight of that liquid is equal to the force of buoyancy. Okay, so this is something that you have learned as well, and you have used this to solve a lot of interesting problems in fluid mechanics. So as a quick question, you can think about the idea that if you want to quantify the change in your weight, so if you stand on a weighing scale in vacuum, and you stand on a weighing scale in your room on Earth, then will there be a difference? And if you think there will be a difference, what will happen to your weight if you stand in vacuum as compared to your weight in normal environmental conditions on Earth? So just food for thought. To quantify it, not just think about it if it decreases or increases. Talk about how much the amount of that change would be. And this is for food for thought. Think about it later when you have some time. Right? Then we also have talked about, in your school, you have learned about the idea of compressibility. So there are fluids which compress when you increase pressure. So when you apply pressure, then the fluid will compress. So air is highly compressible, whereas water is almost incompressible. But if you go beyond 50 atmosphere, even water will start showing some compression. So there will be some volume change. So you had this coefficient of expansion or compression that you have learned about. And fluids like water, which are incompressible for a range of pressures. So if you're talking about a pressure of between 1 and 10 bars, then water will almost have no or negligible change in volume. So you can assume it's almost incompressible for those range of pressure values. Right. So this is in terms of statics. Then you have done some dynamics as well. This is some dynamics. So that was in dynamics, you talked about the idea of viscosity. Where a relation called shear stress tau is equal to a coefficient called mu, that's a coefficient of viscosity, times du by dy. So what we're talking about here is, so this tau is shear force acting per unit area. So if you have, let's say, a channel, so you can think of these as two plates, one over other, and one plate is stationary, the other one is moving. So for to move that upper plate, and of course it's filled with liquid, so they're very long infinite plates, uh, and this force you are applying on the top plate to move it with a certain velocity u. So the upper plate is moving with a velocity u. Let's call it u infinity. And the lower plate is stationary. So the fluid that is contacting the lower plate is stationary. So what you see is, there is a velocity distribution with height. So if this coordinate is y, then you get u as a function of y. So from this you can calculate du by dy. So this u as a function of y will give you du by dy. And of course, F shear is something that you are applying. So viscosity basically will tell us a link between F shear and du by dy. So if you have a more viscous fluid, like honey, for example, then for the same shear force, you will see that du by dy will be different. If you're talking, I mean, in this case, we're talking about a special case here, where the dependence is not there, but in general, that dependence is there. This is more of a geometrical problem. But in general, if you have, if you talk about this equation, then for the same shear stress, you would have a different du by dy depending on the viscosity values. We'll talk more about it in terms of quantifying it, but this is the idea of viscosity. And we have this idea to generate the same this du by dy. We'll need a larger force if we are working with honey, and a lesser force if you're working with air, for example. Air is much thinner in terms of viscosity. So that's the idea of viscosity that we have been introduced very briefly about. The other is the idea of ideal fluids or inviscid fluids. So you learned about this idea of inviscid fluids, that is no viscosity. It's ideal. Ideal fluid basically means that the fluid has no viscosity. So you learned about this when talking about Bernoulli's equation. Bernoulli's equation is valid for ideal fluids. Although no fluid is ideal, but some fluids are closer to the ideal fluids as compared to others. Then you have heard about the idea of steady flow. So if I take a pipe system and switch on the pump, the water starts to flow. So I will see that if I was to measure the flow at a given point in pipe using some pitot tube, then I plotted this x velocity with time. I would see that initially it's 0, then it starts developing, and then after some time it becomes constant. It does not change with time. So what that means is that beyond this point in time, the flow became steady. So we say steady flow is flow for time tending to infinity. After a very long time, the transients have died away and the flow variables are not dependent on time anymore. They have become steady. They are not unsteady anymore. Another idea is about rotationality. Okay, so I mean, this was just, I think many of you may not have even have heard about it. So rotationality is a very general idea where, for example, if there's water flowing in a river and suddenly you see that there's a rock that is obstructing the path, So you will see that the water goes around it, but then you see a lot of rotational eddies kind of thing that gets generated. Some froth gets generated, some eddies. So again, next time you go near a river, then do notice these rotational effects that get generated when you have some obstruction in the flow of uh, smoothly flowing water. This is an idea that you have heard about, but we'll of course expand it in a much more quantified way in this course. Then the idea of streamlines. So these pictures that you have seen, um, even that Van Dyke book that I showed you. So streamlines, you've seen these pictures where such streamlines are drawn. So when these streamlines are basically those lines where if you draw a tangent, that is the direction of flow velocity. So here, for example, the direction of flow velocity is like this. Here it's like this, and so on. So streamlines get closer to each other when they are passing close to a body and so on. And so this idea you may have seen, or at least you've seen pictures related to these things. Okay. So I'm simply recalling those H.C. Verma ideas or NCRT ideas that you've seen in the 12th class or JE preparation. Conservation of mass. Okay, so if you have a nozzle and there is fluid flowing through it, then what will happen is if the area here, the area of cross section, let's say this area is A1, the area here is A2, and the speed was V1 here, and the speed is V2 here. So we definitely know that V2 is going to be higher than V1. In fact, we can, if the fluid is incompressible, we can write A1 V1 is equal to A2 V2. Okay, so this is conservation of mass. Because the same mass has to travel through a smaller cross section area, then the speed has to increase. Okay, and that is the reason if you decrease the cross section area, the speed of fluid getting released will increase. Right. Then we have you have learned about normal stresses or pressure. I mean, I already should have talked about it. So the idea, we actually have discussed. I was going to talk about change in volume because of compression, but that we just talked about in compressibility issues. Okay. Right. So this is typically what fluid mechanics has been for us. So I have got a couple of problems for you from this book called Aerofoil, okay, just as a practice. Let's see if this is there. Right. So one thing that right. So let's see if I have those problems. Yes. So I've put a couple of problems here. So please practice them. So there is a problem of pitot tube here. Then there's a problem of viscous fluid and how you can solve problems related to that. So as the flow happens through a pipe, it loses some energy and because of viscosity, and then you can see that the static pressure is much smaller that you're measuring using these some sort of a manometer, and then you have this problem where you have a disc surrounded by oil. So there you have to calculate the torque to rotate it with a particular angular frequency. Okay, so these problems are 12th standard problems or JE problems. So just put a few of them for you to practice and revise your old skills. Okay, so this was a quick recap of what fluid mechanics has been for us. So now we'll start with the new stuff. Any questions before we do that? Right, so I'll call it new ideas. So the first idea for today is called Continuum, first new idea, Continuum Concept. It's a very important concept, and one must understand it to appreciate the scope of applicability of the fluid mechanics that we are learning in this course. So in reality, we all know that matter is discrete in nature. You have atoms, and these atoms fill the space around us. Okay, so we all know that. And let's also talk about what sort of engineering scales we are working with. So let's say we are solving a problem on flow past a Formula One car. Then what's the smallest of the smallest volumes that we'll want to consider? Let's make it very small. So let's make it, no, 1 millimeter is pretty small, but let's even go 100 times smaller. So let's say that the smallest scale I would want to go to is 10 micrometer. Okay, so that is equal to 10 times 10 to the minus 6 meter. Or that's 0.01 millimeter. So 0.01 millimeter is extremely small. Can't even draw it using my pen because my pen, the line I'll draw will be thicker than that. Of course, you would never want to think of a scale smaller than that. So let's work with this as a smallest scale. So if I draw a cube of a size of 10 micrometer, then at standard temperature and pressure, I would have of the order of 10 billion molecules of gases, 10 billion in this volume, in this hypothetical volume, that the cubical volume that I've thought about. 10 billion is what we're talking about. And if I was to calculate, or let's say I would want to say that the center point of this cube is point P. So this cube is centered around, so this cube is has a center at P. And I want to define point properties. So what that means is I would want to define the temperature at the point P. So what I'll do is I'll average the temperature of these 10 billion molecules surrounding the point P in this hypothetical volume of 10 micrometer side. So I can define as average over the cube molecules. Okay, so this is what the continuum concept is, that although the matter is discrete in reality, although this cube will be having mostly void space, Okay? Mostly it will be void. Even though it has 10 billion molecules, the molecules are so small in size that if you were to randomly put points, most of them would be in empty. There'll be no molecule at that point. So the space in reality is not continuous; it is discrete. But we come up with this continuum concept as a hypothetical concept. As what we say is that to define a property at a point, we'll average the properties of the molecules in a cube of a certain size, certain small size. So that will help us define point properties. Okay. So this could be these properties could be temperature. So I could average the temperature of those 10 billion molecules. Pressure, average the pressure of those 10 billion molecules. Velocity, again find the velocity, instantaneous velocity of each and every molecule, and then average it for the 10 billion molecules, and so on. So now theoretically our space has become continuous. You can go to any point from one point, and then you can define these properties. So if I was to plot the temperature as and some x coordinate, let's say this is my x coordinate. So if I go along x, I can plot the temperature using this idea. So at any point I would want to plot it, then I can find the average in a cube of 10 micrometer side. All right. So whatever theory we develop in this course, whatever we discuss in this course, will assume that the continuum concept is valid. So the equation that we will write will assume that these properties are continuous in space and time. Okay, until we reach the idea of compressible flows. There discontinuous will occur, but other than that, everything will be about assuming that these properties are continuous in space and time. Okay, so if you were to apply these properties after you go to, let's say you start working in an industry where that designs vacuum chambers. So there the idea is that you remove as many molecules as possible from this chamber. But there these ideas will start failing at very extremely low pressures. Extremely low pressures mean extremely small number of air molecules that are present in the chamber. So what will happen is that if you start drawing these hypothetical cubes in the vacuum chamber, you'll see that you'll have very few molecules. So the average will not be a very good average. So if you move from one point to the other, then suddenly you'll see discontinuous jumps in properties because the number of molecules you're averaging is very small. Okay, so there the continuum concept will fail. So before applying these equations or these ideas in a general sense, always remember the starting point, the idea of continuum concept, that these properties, this theory has been developed for assuming that the continuum concept is valid. So there is a non-dimensional number called Knudsen number, denoted by Kn. So this is written as lambda upon L. So lambda is called the mean free path, and L is a characteristic length. So what this means is, so if I'm talking about a room, so let's say I'm trying to do fluid mechanics in flow inside a room. So my room has a dimension, a characteristic dimension L, which is approximately, let's say, 1 meter. 1 meter is very small. So let's say 10 meters is the size of the room. So L becomes 10 meter. And lambda, mean free path, is defined as the average distance traveled by a molecule before it hits another molecule or hits the wall. So if you have a lot of molecules in the room, then the average distance a molecule will travel before it has a collision will be very small. But as you keep removing the molecules from the room, the number of molecules decreases. So on an average, a molecule will travel a larger distance. So basically, this lambda will be dependent on the density of packing of the molecules in the room. Okay. So if you're talking about lots of molecules inside a room, that is what happens typically, then your lambda will be very small. So lambda is basically inversely proportional to the number of molecules, the density of molecules in a room. Okay, so this ratio lambda upon L will tell us the density as such of the molecules. So in a real situation, your lambda by L, the Knudsen number will be extremely small, which is good. So what we say is that this Knudsen number is used to understand whether the continuum regime is applicable or not. So typically we say if Knudsen number is less than 0.01, then the continuum concept can be applied. Just a ballpark figure, but try to keep it much smaller than that for a safe application of this regime. But again, in this course, don't even think about it. I mean, most of the situations we work with, this regime will be valid. Any questions? If there's no question, then we'll move to the second idea. And this idea is about theory versus experimentation. So any engineer who works in the industry will attack a problem from two. There will be two approaches to attacking a problem. One is theoretical ideas. Just a second. Sorry for that. So theory versus experimentation. Okay. So whenever you start attacking a problem, then you would go to theory, because theory will not require any experience in that field in the sense that you will not require any data. Okay. So what do we do in theory? We use conservation laws. I'll say elegant conservation laws. So law of conservation of mass, law of conservation of momentum, law of conservation of energy, and so on. Very elegant in the sense that they can be applied in a general sense. You don't need to have any experience in that field. If the field is new to you, you can again apply the laws of mechanics and come up with some theoretical um, predictions. But there are lots of assumptions here. So it's what that means is that you would you have to assume, for example, in mechanics, you would think the point mass mechanics, or even if you have a block, you would assume that the block is of size 0, so no rotation effects and so on. So you would have some sort of assumptions. One has to be careful about those, and under those assumptions, only these theoretical ideas will be valid. Whereas on the experimentation side, if you were to conduct experiments on let's say let's take an example here of aerofoil. So you have an aerofoil, and the flow is happening over. This is the wing of an aeroplane, and the flow happens past a wing. So the flow goes like this, and then below it, it goes like this. Okay. So theoretically, you can calculate what sort of forces will this flow apply, and experimentally also you can measure these forces by figuring out the force you have to apply to keep the wing stationary if flow is happening past it. Okay. So in an experimental situation, you'll have real world constraints. So lesser number of assumptions here because you're talking about the real thing here. Although it may be a smaller scale down experimental system, but still it is much more real as compared to theoretical calculation or theoretical model. But as I said, these are always first level calculations. That's the first way to attack a problem. But once you get some estimate, then after that, if you have more time to work on the problem, then you would go for experimentation. Because experimentation would require you to construct that, make it from the right materials, and then install lots of sensors and actuators and so on, and then you can conduct the experiment. Theory is more general. Okay, so what I mean is, if the theory is for a given shape, I can always change the shape, and then since my equations are based on first principles, then they will work for any shape, any cross section, and any material, any fluid type. Whereas experiments are not general; they're restrictive. So if I do an experiment for a given shape, that result, that graph of force of drag versus speed of flow will not be valid for a newer shape or a different size or a different material or a different fluid. So you see that experiments are restrictive. So there's no generality as such in the experiments. Although we'll talk about extracting some generality out of it using the ideas of dimensional analysis, but still they are restrictive in nature. But they're highly accurate. And detailed. Okay, so these experiments are useful for scaling ideas. We'll make a smaller setup, and then the ideas of scaling that we learn will allow us to apply whatever learning we have got in terms of drag force, let's say with velocity, and then I can apply it on a larger scale. Although the drag force will change, it won't be the same for a larger scale, but I will know a way to transform those small scale results to large scale experimental or large scale prototype results. So that will allow us to go from component scale to device scale results. Okay, so this is there are two ends of spectrum. One is theoretical approach, the other is experimental approach. And this course, we will be moving from theoretical to experimental to theoretical. So we'll be jumping from one idea to the other to refine our understanding. And as you know that even though experiments are conducted so what we do is typically we start with theoretical ideas. We develop some relations. So in your 12th standard, you learned about the Poisson flow. So that's a relation between the pipe radius and pressure drop. The pressure drop and flow velocity. So this relation you learned in your 12th standard, that was given to you. You simply have to use it. So in a pipe, if you apply a pressure difference, then what flow speed will get generated? So it's dependent on, it's a function of radius, it's a function of viscosity and so on. So this relation you've learned. So this was obtained from theoretical principles. But when you do a test using experiments, you will see that it works for some range of velocities, but beyond that it stops working. So when you think about it, what may be happening at larger velocities that these results are failing, and then you refine the theory based on those experiments. So then you think that, okay, my theory had an assumption which I didn't think about. Let's remove that assumption. Let's make it more general. It's a continuous process where you refine your theory based on results from experiments and so on. Continuous improvement that happens. Okay, so that is what we will learn in this course as well. We start with some very basic ideas, learn some experimental results, standard experiments conducted in the past, benchmark experiments as we call them, Reynolds experiment and so on. And then we will see that, okay, there is some change that was done to the theory. So we'll also refine the theory as it has been done in the past. And then come up with a more general theory. so to say. Okay, so we'll stop here, and I'll continue this introduction in the next session that will happen on Tuesday. So that will be we'll need one more lecture on introduction, and then we'll move to fluid statics. If you have any questions, I'm happy to answer them.